Snow. Food for a poet, fun for children, but problems for the aviation industry. Snow falling on the ground at a temperature of 28 degrees or below will pack. Like any dry bulk, loose pack commodity, it can be easily disposed of by shoveling or sweeping. For this reason, the only problem this type of snow presents for airport operations is clearing of runways and terminal areas. However, as the temperature rises, the snow begins to melt. The color changes from white to gray. The water content for any measured amount increases. Its specific gravity approaches that of water. Because of the higher specific weight and the fact that it no longer packs, slush creates serious hazards for aircraft operations, particularly for propeller-driven aircraft have operated from slush-covered runways for years, observing only the necessary additional ground run and, of course, slush freezing in the gear or flaps. After becoming airborne, in an attempt to overcome this latter problem, pilots often recycle gear and flaps once or twice. The attendant problem of additional ground run has not been as acute. In only one case has the failure of a prop-driven aircraft to attain takeoff velocity been directly traceable to slush, and that was when the slush was reported to be 5 inches deep on the runway. The ability of propeller-driven aircraft to deal with slush is due primarily to prop aircraft having a relatively high thrust-to-weight ratio, a low tire pressure, and a low takeoff speed. The pressing problem is that this ability is unavailable in the operation of jet aircraft. Because a comparatively long ground run is necessary under normal conditions, any increase in the takeoff distance resulting from slush creates a serious problem. Due to an operational incident in March 1959 and evidence of damage to an airline jet transport operating in slush, the Federal Aviation Agency issued a rule that prohibited jet aircraft from taking off on runways with any measurable amount of slush. A relaxation of this rule was not effected until the results of various tests conducted by the National Aeronautics and Space Administration's Research Center, Langley Field, Virginia, and by a prominent aircraft manufacturer were presented to FAA for consideration. Shortly thereafter, the FAA issued a new rule stating takeoff shall not be permitted when standing water, slush, or wet snow greater than 1/2 inch in depth covers an appreciable part of the runway. This rule is still in effect. Jet aircraft can be excellent revenue producers, but due to high initial cost and operational expenses, they represent a serious loss potential when grounded because of weather conditions. Researchers and engineers at NASA and elsewhere were busy experimenting in an attempt to work out go or no-go formulas for slush operation. These formulas were based on tire width, aircraft weight, slush depth, thrust-to-weight ratio, and takeoff velocities. What was needed now was a full-scale test program under which conditions could be controlled and measured accurately. The FAA's National Aviation Facilities Experimental Center, located at Atlantic City, New Jersey, was assigned this task. The program was designed to determine the following: slush drag forces, incipient damage boundary, spray patterns, aquaplaning characteristics, all in relation to aircraft velocity and slush depths. It was felt desirable that a 4-engine jet aircraft, representative of the type being flown in current passenger service, be used in these tests. The program was started with the delivery of a Convair 880M to the FAA. Runway 1331 was selected for laying test beds of slush 50 feet wide and from 1,000 to 3,000 feet long. This central location was selected to permit enough room for the test aircraft to accelerate, to have enough room for engine spin down to idle thrust, to allow sufficient distance for the aircraft to brake to a stop after exiting the test bed, or to be able to accelerate to a rotational velocity for takeoff. Primary measurements of aircraft position, velocity, positive and negative acceleration, and attitude were obtained by phototheodolite and accelerometer instrumentation. The first test in slush was scheduled for late September. Ice was delivered to the runway site in the early morning hours in huge insulated trucks. The amount of ice required for the entire project was 2,300 tons, enough to lay end to end a solid lane of 300-pound cakes 12 miles long. The cost seemed expensive, over $50,000, but not if one consider that the washout of one jet aircraft amounts to $5 million. While the leveling operations were being conducted on the test bed, preparations were begun on the 880. The aircraft was fueled and towed to the starting position. Towing assured that the combined aircraft weight, including fuel allowance for burn-off, would remain constant at approximately 150,000 pounds. As the sun came up, the test preparations took on a feverish pitch. The test bed must be leveled and waiting for the sun's warmth to turn the snow ice into slush. As the snow ice was laid, it was leveled much in the same manner as concrete, that is, by scrapers riding on leveling boards. But unlike concrete, the snow ice would not shear easily. Leveling was a tough job. Then began a period of critical balancing of all factors by the task team. Constant measurements were begun. Slide rules, rules of thumb, estimates, experience. Start too soon, you won't have the right aircraft weight due to fuel burn-off. Balance. Information from density measurements. The snow ice is becoming slush. Now. After braking to a stop, the plane was inspected. Damage to the basic airframe from the slush spray was relatively minor. However, components of light construction received considerable damage. The slush stuck where expected, on wheel axles and bogies, flaps, and where we might not expect it, in one of the rotating beacons. A considerable amount of slush was found to have passed through the air conditioning inlet plenum and had accumulated inside the special fabrication designed to house photo instrumentation cameras. Accumulation was relatively light because the tests were conducted in warm weather. The aircraft was warm, the slush bed short. Operations on long runs in slush during freezing weather would result in greater accumulation. Slush freezing in flaps and wheel wells during climb to altitude is an additional problem to be considered by the pilot. To understand the problems of slush accumulation and impingement, it is necessary to understand the various spray patterns and behavior of the aircraft wheels. 3 well-defined sprays can be observed from the main wheel bogies. The bow wave, slush spray ahead of the rolling wheel. The side wave, slush spray extending from either side of the tire. The rooster tail, slush spray developed by the interference of the 2 side waves of the side-by-side wheel configuration. We first see the wheels at a speed of 10 knots. Slippage of the forward wheel is noted by the revolutions per second indicated beneath each wheel. At 30 knots, the side wave is growing and moving aft, approaching the vertical. The bow wave moves further forward and increases in height. The rooster tail begins to grow and spread out. At 50 knots, the bow wave begins to separate from the side wave and reaches a maximum height. Also, the relative amount of forward wheel slippage increases. 80 knots, the side wave moves in a direction slightly aft of the vertical. The separation of the side wave from the bow wave is more distinctly shown. Increasing to 105 knots, the bow wave extends a maximum distance ahead of the wheel. Here, slippage of the forward wheel is considerable, while the rear wheel rotation is nearly the same as would occur on a dry runway. The rooster tail is now beginning to level off. When the aircraft reaches a ground velocity of approximately 115 knots, the forward wheel no longer contacts the runway surface and aquaplanes on the slush. Considerable forward wheel slippage is still evident. At 130 knots, the side wave and rooster tail are more shallow, and the direction of the spray almost horizontal. Also note that the forward wheel starts to spin up. At 140 knots, the bow wave completely disappears. The rear wheel becomes readily visible. The forward wheel continues to spin up. When the aircraft reaches a ground velocity of 160 knots, the side wave and rooster tail are extremely shallow, and the forward wheel almost spins up to the rear wheel. For a runway covered with slush to a depth of 1 inch, the relation of the slush drag force to the ground velocity of the test aircraft is illustrated. As the aircraft increases in velocity, the drag force from slush increases in direct ratio to the square of the velocity. However, at speeds above 120 knots, the drag forces decrease. And this decrease is due to the fact that at speeds above 120 knots, the tires aquaplane. This results in a lower drag force from the wheels, as well as the lowering of slush flow and the consequent slush impingement drag. The increase and then decrease in the slush drag force as the velocity increases may be illustrated by the patterns in which the slush sprays from the wheels. As the aircraft velocity reaches 105 knots, the slush drag force is increasing. Motion picture coverage of a test run at 105 knots shows that the nose wheel, rooster tail, and side wave force a large amount of slush toward the bottom fuselage and Kruger flaps on the leading edge of the wing. The heavy vertical and lateral slush displacement can be easily seen. In later and much higher speed runs, this heavy displacement will be reduced because of aquaplaning. At this speed, wing root-mounted engines would experience heavy ingestion. Again, the substantial impingement against the inboard wing section and fuselage from the side wave and rooster tail of the nose wheels can be seen. Note that the engines are free of slush ingestion. This aerial shot shows the slush flowing over the wings from the nose wheel spray. Note that the nose wheel side wave does not extend beyond the inboard engine. As the aircraft accelerates beyond 105 knots, the slush drag force increases to a maximum at approximately 120 knots, but decreases as the aircraft approaches 130 knots. At this velocity, the bow wave is comparatively small. Only a slight amount of slush passes over the wing, although there is considerable underwing and fuselage impingement. The slush, in both lateral and vertical throw, decreases. It is still throwing short of the inboard engines. In this view, the decrease in the bow wave permits the nose wheels to become visible. An aerial shot of this test shows little throw outside the test bed area, but a probable ingestion problem for aft fuselage mounted engines. As the aircraft speed reaches 150 knots, the slush drag force continues to decrease. The bow wave now completely disappears. The flow of slush is almost horizontal, just reaching the under fuselage and wing. At this speed, the aquaplaning and resultant decrease in slush flow permits the main bogies to become visible to the camera. There is still considerable flow along the fuselage, back to the vertical and horizontal stabilizers. At a speed of 150 knots, the effect of aquaplaning causes further reduction in lateral flow of the slush. Then to another study, the relationship of slush depth to the slush drag force. Results of a test conducted at 110 knots with a slush depth of 3/4 of an inch indicated that the slush drag force was 13,200 pounds, more than the takeoff thrust of one engine. At this depth, the entire airfoil, including the inboard leading edge, is visible, even though the spray from the nose wheels is causing flow over the wing root areas. Here, only an occasional flow over the Kruger flaps in the inboard wing section is visible. The flow can be described as comparatively light. This view gives the best indication and comparison of slush spray density and resultant drag and impingement values. As the depth increases to 1 3/8 inches, the slush drag force increases to 22,900 pounds, nearly equivalent to the loss of 2 engines. Spray over the Kruger flaps is seen from the side wave of the nose wheels from coverage of a test under these conditions. The wing area inboard of the engine is still visible, although evidencing considerable increase in the slush flow. Compared to the preceding test at the 3/4 inch depth, spray over the wing is seen to be heavier, as could be expected. As the depth increases to 1 7/8 inches, the slush drag force becomes 33,400 pounds, nearly equivalent to the loss of 3 engines. In this dramatic shot, taken during a test under these conditions, the increased depth is now causing heavy impingement of slush under the fuselage and completely obscuring the wing inboard from the engines. The engines still show no evidence of slush ingestion. Wing root mounted engines would be exposed to considerable slush ingestion. The main flow toward inboard wing sections and flap areas is created by the nose wheels. Again note, flap impingement as well as throw over the wing. The density of the spray substantially increases. In an effort to determine the amount of drag contributed by the nose wheels to the overall drag force, a special test was run at a speed of 105 knots through a slush bed 1 3/8 inches deep. The bed had a slot for the first 500 feet in which the nose wheels ran free of all slush. The results? Approximately 1/3 of the total slush drag is caused by the nose wheels, 2/3 by the main wheels. These drag forces were almost 3 times that predicted as a result of previous studies for the nose wheels, almost twice that predicted for the main wheels. Based on the results of test runs at idle power, the relation of velocity to position was predicted for the test aircraft operating at maximum takeoff power in slush 1 1/8 inches deep. Plotting this predicted relationship, allowing distance for acceleration to 100 knots on a dry runway surface before entering a 3,000-foot-long slush bed resulted in the curve shown. The dots represent the velocity history of an actual power run through the bed under these conditions. This validated the method of testing with engines at idle power, which was much safer and a more accurate procedure than test runs at takeoff power. How does the additional drag of the slush affect takeoff performance? On a standard day at the test weight of 150,000 pounds, the 880M operating on a dry runway can be expected to reach takeoff velocity in a distance of approximately 3,400 feet. If the runway is covered with a 1/2 inch of slush, the predicted distance increases to 3,975 feet. When the depth of the slush is 1 inch, the distance will increase to 5,000 feet. When the slush is 1 1/2 inches deep, the distance to reach takeoff velocity will be almost 2 miles, 9,525 feet. This is almost a 200% increase. At a depth of 2 inches, the aircraft cannot accelerate beyond 110 knots. The retarding forces now equal the available thrust. Since this velocity is far below that required for liftoff, no matter what pilot techniques are used, the takeoff distance becomes infinity. Another problem associated with slush is that of stopping the aircraft if an emergency requires aborting the takeoff. The surface is slippery. At the higher speeds, forward wheels spin down, and the tires are aquaplaning. The result? High-speed braking is almost non-existent. Low-speed braking is greatly reduced. For example, the distance required for stopping the test aircraft from a speed of 100 knots on a runway covered by a half-inch of slush without using reverse thrust is approximately 3 times the dry runway stopping distance. This full-scale test program answered many questions concerning the operation of jet transport aircraft from slush-covered runways that previously had either remained unanswered or had been answered by assumptions. We know that the retarding effect of slush can greatly hinder the takeoff performance of jet aircraft. A substantial amount of slush impingement and accumulation is likely to occur. Slush ingestion into wing pod mounted engines is unlikely. A slush ingestion problem may exist with aft fuselage and wing root mounted engines. The nose wheels contribute a significant portion of slush impingement damage and slush accumulation. Prior methods of predicting the retarding effect of slush were inadequate. Finally, tire aquaplaning in slush reduces the slush drag force. Results of these tests do not suggest any relaxation in the present FAA rule of prohibiting the operation of jet aircraft in slush at depths greater than a half-inch. It is the Federal Aviation Agency's sincere hope that this intensive slush test program will serve to better acquaint the aviation industry with the potential hazards of slush on jet aircraft performance.